In this video, we will explore the expectation value definition and its applications. In the classical physics, it is normal to define the position and momentum by using functions of time. Actually, it is usual to have a single defined function for each of them. On the other hand, in quantum mechanics, position, momentum, energy, and any measurable magnitude of a system is represented by operators instead of functions. As we stated before, the classical physics, position and momentum are determined by solving the equation of motion. On the other hand, in quantum mechanics we can know, at much, the wave function. This means that we have only the probability to find any measurable of the quantum system. However, we can take advantage of the statistical nature a set of many individual quantum systems, by defining the expectation value with the following formal definition. Notice that A is an operator as mentioned before. Also, the product of the wave function times its complex conjugate, it is simply the probability of finding the quantum system in the operator, A, at some point of position and time. Now, we need to understand that the definitions of position, momentum, and kinetic energy have specific forms on the quantum theory, as mentioned before. Though, these definitions should be consistent with the classical physics. We are not going to show how the operators are deduced as it is out of the scope of this course. However, their definitions are the following. The position operator is the simplest one. It is defined as the simply, x. On the other hand, the momentum operator is defined as follows. Note the derivative with respect to the position. Actually, this is on x, due to the one-dimensional nature of the motion we are studying. Actually, in the case of a three-dimensional case, the derivative becomes a gradient. Finally, the kinetic energy operator is defined as follows. As before, the second derivative is over the x direction. It is important to notice that each of these definitions will be reduced to the classical case when the appropriate conditions are set in the systems. Now let's focus on the expectation value of each of the aforementioned operators. The expectation value of the position is defined as follows. In the same way, the expectation value of the momentum is defined in this way. Finally, the expectation value of kinetic energy has this definition. As can be seen, the expectation value has a quite simple definition. Though, it can become challenging when the wave function is a complicated one. Let's solve an example to see how the expectation value is calculated. Example 22. Determine the expectation value of position and momentum if a quantum system has the following wave function. Assume that the wave function is defined from 0 to L. Could you solve it? Answer. We know that the definition of the expectation value is this. Also, the wave function is defined as follows. If we substitute the wave function into the expectation value definition, we get the following. Note that as the wave function is real, then its complex conjugate is the same function. Performing the integration, it is easy to see that the resulting expectation value for the position is simple, the value of L divided by 2. This means that the most probable place to find the quantum system is actually L divided by 2. Now, in order to calculate the expectation value of the momentum, we need to insert the wave function in the definition as follows. Here it is very important to notice that the derivative is applied only to the right function, it is, the original wave function. Again, performing the integral results simply in 0. This result is interesting as it means that the quantum system spends the same amount of time moving to the left and to the right. If we now calculate the probability of finding the system at x equal to L divided by 2, we get 1. Meaning that the most probable place of finding the system is exactly this, as stated by the expectation value. In the next video, we will discuss a vital part of quantum mechanics, it is, the Schrödinger equation. Stay tuned.